Okay. Ha! It's fun to never rehearse the stuff. I never knew I would just jump up and down and land in my place and belt out like that, like a karate move. I'm Robert Adut. This is yaymath.org. New edition, next generation. I still haven't figured out what I'm going to call it, but it's next something. And we're going to be talking about how to solve equations. In order to do that, we need to also define some terms. Now, I'm going to be very honest. I actually am not a huge fan of vocabulary. I think it serves its purpose, but the over-reliance on it has been something that's really been burning a lot of my students, and they don't like it because there's a memorization level associated with that, and I'm not a huge fan of memorization when compared to conceptual understanding. I'd rather we conceptually understand stuff. So I will go through the vocabulary because I know it's important for people. I'm with you in saying like, in that regard. But I will try to find some silver linings within here that make it feel like, okay, it's not so bad, and we could just move forward through it together, all right? So this is the first property of all mathematics. It's called the reflexive property. That's basically saying like any number, let's say x, equals itself. That's it. Kind of weird that there's an actual rule for that. What I do with my students is I call this the reflexive property, as in when you look in the mirror, you see your own reflection. So this is x looking at him or herself, and if it was a person, and that person would see its reflection, if it's a thing now, like a dog, but that's masculine and feminine too. I'm getting ahead of myself. Either way, when you look at yourself in the mirror, you see a reflection, and that's the reflexive property. Next is the symmetric property. This is all it is. If you can conclude that like a equals b, some value a equals another value b, then based on the rules of algebra, you're allowed to say that b equals a. I get that. I know that. It's weird that this is a rule and that people are held to this sort of standard for testing in this regard, but I just wanted to give it to you so that you know what it is. The way I remember it is like if you think of the human body as more or less symmetric, more or less, like you think of like that Da Vinci thing. And so that would mean the left side of my body is the symmetric same as the right side of my body. So I can reflect this side over that, and it's pretty much the same. So if I reflected the A over here to B and the B over here back to A, it's the same equation in a sense. I'm allowed to do that. I'm allowed to reflect symmetrically over the equal sign, over the dividing line. All right? Transitive property. When I think of transitive property, I think of the train. Transitive train. Here's how it goes. Let's say I start at stop A, and then I go to stop B. Get off. And then at stop B, I go to stop C. Get off. Is it safe to say that I started at A and ended at C? So I think of the train. Stop A to B, get off at B, get on at B, go to C. That means that A connects to C. And it's totally true. It makes sense logically. Substitution is a weird one. Basically, if you take something out and substitute something in its place, that's all it is. So if you said something like this, let's say 6 times 2 times x equals 20. Right? Separate these. If 6 times 2 times x equals 20, we're also allowed to say the equivalent statement to that is 6 times 2 times x is actually 12x equals 20. Stay with me, board. I know you have a life of your own. I thought I'd be losing the life, but I actually get an inanimate life through you. Yes, so 6 times 2 times x equals 12x. So this was taken out, and in its place, this was put in. 6 times 2 times x was taken out, and 12x was substituted back in. Okay? Some people get this confused with multiplication, all right? We're going to make that differentiation, because I agree that we're doing 6 times 2 times x is 12x. Here's the difference when it comes to multiplication. And this is how tests get tricky for some students, is that all these four, these basic math ones, has to do with when you do something to both sides of an equation. And we're going to have that conversation next. So this is what I mean. If like A equals B, then it's also safe to say that if you multiply both sides by the same thing, then it's also true. It's also true. So let's say I multiply both sides by 4. I would get 4a equals 4b. See the difference between these two? Indeed, I am, technically multiplying 6 times 2 to make 12. However, I didn't do something to both sides. The multiplication property, or multiplicative property, whatever you want to call it, is if you do it to both sides. And this is all the same here with addition, subtraction, division. So we can even stick to our theme of a equals b. If I added something to both sides, sometimes I like to do this, puts a little color in, let it pop, right? So now we can add 4 to both sides, plus 4. There you go. I added 4 to both sides, that's the addition property. Subtract 4 on both sides, that's the subtraction property. And then divide something on both sides, a over, mix it up, 5. Very good. So whatever you start with and then do something to both sides, that's one of these math properties, okay? Now we're going to put these to the test, and in fact, I'm going to get to something a lot more fun, which I've been dying to share for a long time, years, literally years. Literally years, I want to share this with you. So 2x minus 1 equals, let's say, 13. So the question is, what is x? What is x? What is the unknown number here that would need to be plugged in to make this equation true? And what's really cool is when I work with like 6th graders and stuff like that, they'll actually, since they don't know algebra necessarily, what it means, because we're going to talk about that in a second, they'll actually try to figure it out. They'll try to, I don't know, like massage it so that x comes to the surface. They'll be like, well, if I make x like 10 or something, that would be 2 times 10, which is 20. We can even write that. Minus 1, and that's 19. That's not equal to 13. So that's an issue. So it's not 10. And then you could also conclude, oh, maybe it's actually a little too big. If x were 10, this side's too big. So we have to think about reducing x so that it starts to match up. And I'm bringing this up for a purpose because we're going to jump into hard Algebra 1, Algebra 2 stuff, and we can't lose track of what we're trying to do here. We're trying to find the hidden number, what x is, to make this equation rebalanced. And that's what algebra means. Algebra is an Arabic invention for restore and rebalance. So what I like to think of is I like to think of a scale. I don't know whether it's because I'm a Libra and that is a balance scale symbol, but this image resonates with me. If you think of a balance scale that has perfect weight on either side, it's completely balanced. That's called equals. The two sides, forget about the stuff in my hand right now because that's funny. The two sides are like perfectly balanced, and so the weight is the same on both. But if you started to add something on one side, it would go like this. But would it make sense that if you had your standard balance scale, if you added plus 5 pounds here and plus 5 pounds here, wouldn't it make sense that, let's say you added 5 pounds on one side, it would go down, and then you added 5 pounds here, and then it would realign. So that means that by the laws of scales, by the laws of balance, whatever you add to one side, if you replicate that on the other side, if you do the same thing, it rebalances. And that's the rule for anything. You could add 5 pounds to both sides. You could subtract 5 pounds to both sides. All those math properties that we did. You can divide the weight by half. As long as you do it to both sides, then it's going to be the same. And that's what we're allowed to do basically for the rest of our lives, doing algebra. Okay? We can do what we can to get this x by itself so that we'll retain balance and uncover what x is. So what I'm going to do is I'm going to add 1 pound to both sides. Let's say I did that. If I added 1 over here, the balance would be out of scale. And that's what actually happens. A lot of students, when they're learning this stuff, they don't think it's such a big deal. And they forget. They're like, oh, boom, add 1. And negative 1 plus 1 is gone. But that's sort of like saying if you have a balance scale and you add 1 to both sides and it goes like that, it's no longer in balance. that sorts, even for me, it's like when I go like that, it's like, something's wrong. I need to do the same thing to the other side. So they're forgetting about the importance about keeping the scale in balance. And that's what we're going to do for many, many, many different times. So I need to add 1 to both sides, and now the scale has balance again, which is kind of interesting. So then -1 plus 1 goes away, and we're left with, if 2x minus 1 is the same as 13, then that means that 2x equals 14. And now it's actually a lot more straightforward. 2 times some number is 14. And that number, of course, is 7. So we could have done it algebraically like this. 2 times some number is 14. Or we can divide the weight by 2. All right, the scale is balanced. Divide this weight by 2. Divide this weight by 2. I think that makes sense. So if you divide everything by the same thing, I'm still a teacher, so I'm going to goof off and be clumsy and klutzy and drop markers on my feet. It's just a part of my blood type. And you'll get the answer, as long as you do the same thing to both sides. So now we're going to use that again and again. I'll put that there. So let's try it. 2/3 times some number equals, I don't know, 30. Sure. Let's do that. We can do that. 2/3 times some number equals 30. 2/3 times what number is 30? Right? Can we think of it? Well, I guess it has to be maybe a little bigger than 30, because 2/3 times some bigger number would have to result in a 30. So we could maybe come up with that number. Some people can do that right away. You know, are you thinking about it? 2/3 times what number? Like if you have a number and then you split it into thirds and you take 2 of them, that number is 30. It's interesting, right? Or you could do stuff to both sides if you don't see that right away. What if I multiply both sides by 3? I'm allowed to do that, right? I'm allowed to do that. If I multiply both sides by 3, 3 divided by 3 is 1. I'm allowed to do that. And I know this is 90. What if I were to divide both sides by 2? Some students like to do that in 2 stages. Steady. Some students like to do that in 2 stages. They like to multiply by 3 and then divide by 2 once they get that 2x by itself. That's fine. That's fine as long as you're implementing the rules. You're doing the same thing to both sides. In this case, I chose to do multiplication to both sides by this fancy R word called the reciprocal. To reciprocate, 2/3 becomes 3/2. It's actually a J. Cole song. You got me flipping like reciprocals. I like that one. It's like, do people know he made a math reference right in the rap song? It's pretty amazing. Flipping like reciprocals. I'm like, good job, good listening, Jay, in your education. And that's what cancels all this. Okay, so this goes. And again, let's develop good habits. Some students like to put the over 1 because they're talking about multiplying fractions. You multiply across here and across here. Or, keeping in mind that 2 can cancel with 30. 2 goes into 30 15 times. 15 times 3, 45. And it is true. It is true. 2/3 of 45 equals 30. Like if you're at a store and something costs 45 bucks and it was on sale for 2/3 of that price, basically each third is 15, 15, 15, 15. If each third is 15, there it is. 2 of them are these 2, and there's your 30. It's just kind of cool, right? I have to like blaze through this in school to meet requirements, but now I get to do this like immersive with you. I'm going to teach you the same way I would teach my own cousin or my brother or something like that, so that you really understand it like from a deep perspective. Not just the algebra behind it, which can be mindless, but also keeping in mind that 2/3 of some number results in another. As long as you can visualize that at least now, then that's a really good thing. Woo! Survived. I actually tried to catch it on its way down. I should have just let it go. You know, don't be a hero and save your posture. All right, let's jump back in. We're undeterred. We're searching for balance, not only mathematically, but within this lesson. So let's do it. Here's another one. Every year we do a problem like this in school. Students take the long road, which is actually okay. So I'm going to put a big fat if here, if. And now that the easel fell over, I actually came up with a name for it. The name for this easel is Easel E. So this is my boy Easel E. And it's definitely a boy, because that was very ungraceful of a fall. So we're going to say, what is 3x, let's say, plus 7? It's a very interesting question because this is an equation. This is an equation of truth. It's already balanced. There is a value of x that makes this true. What some students do, if you look closely, is that, oh, if they're asking for 3x plus 7, all I would need to do is get x here and solve for it, and then plug the thing into there, right into easel E, and then solve that particular expression, and that will be the result, okay? They love this on the SAT and things like that too, because hidden inside is the same exact thing about rebalancing. I bet that if you look closely at this and this, you can see a relationship between them. In fact, this is a certain number of numbers away from that. Can you think in your mind what I would need to maybe add to this so that it results in this? How far away is, well, you know that 3x is already the same, you see that. But how far is negative 3 from 7? What would I add to negative 3 to result in 7? Okay? And if you said 10, then that's correct. Because negative 3, so let's take this off. I'll show you something cool. Rather than solve for x and get that actual number, we don't even need to know what x is in this particular problem. Because if we use the value of rebalance, if I add 10 to both sides here, check it out. 3x minus 3 plus 10 actually results in 3x plus 7, which is what we're looking for. And so this results in 10 plus 1/4. We don't have to make it more complicated. 10 pizzas plus 1/4 of a pizza is 10 and 1/4 pizza. 10 for me and 1/4 for my friend at the house, because I'm generous. And this is the answer. That's it. 3x plus 7 is 10 and 1/4. Simply by understanding the link between these two and using this concept of balance. All right? Well, my friend. Oh, here it is. Finally, we're going to solve for specific variables. This is a formula for volume, right? It's the volume of a cone, if you're interested. And in doing so, we're following rules of balance again. On this side of the scale is the volume, and on this side is how to get it, okay? What if we said, what is h? Or solve for h? You know, let's write please, because I hate how books are so aggressive. Please solve for h, if you would be so kind. Here it is. We want to get h by itself at the end of the day. Boom. What is in the way of h being by itself? All h's friends, all right? You have 1/3 here and pi and all that stuff. How do we get h by itself? We have to, again, do stuff to both sides, all right? How about this 1/3? What can we do to both sides to get the 1/3 away? In other words, is there 1/3 that could be multiplied by something to make it go to 1? And that number is 3. Let's check it out. If I hit up 3 times, 3 times 1/3 times all this, gone. We're left with 3v equals whatever's left over here, pi r squared h. Okay, again, Do stuff to both sides. Pi and r squared are in the way of h being by itself. So to counteract these multiplication signs, we have to do division signs. Lovely and lovely. Pi divided by pi, gone. Must do it to both sides. Right? We had pizza, now we have pi. R squared divided by r squared, gone. R squared over here. Low and high, and behold, these are gone, and this is what's left. Like a boss, easily stay with it. Pi r squared. Done. Okay? Any questions? I'm still used to asking that. I don't hear any. Okay, so thank you. We'll come back again with the next lesson. Yay, math. Peace. See you soon.